In just a few moments' time, when we dive underwater, this submarine will become essentially invisible.
Carried-in submarines effectively prevented warfare by being so destructive, so frightening, that the concept of warfare between nations who owned them became unthinkable.
The Virginia class is acoustically the stealthiest submarine that the U.S. Navy has ever produced.
When Elon Musk calls something decades ahead of the competition, the world pays attention. Recently, the tech billionaire made a stunning statement about America's newest underwater weapon system, a submarine so advanced, so impossibly quiet, that it becomes essentially invisible the moment it slips beneath the waves. This is the Virginia-class attack submarine, a machine that rewrites the rules of underwater warfare with technology that rival nations can't match. Let's dive into what makes this steel giant America's most powerful secret weapon beneath the sea, the ghost that swims in darkness. Imagine 8 million kilograms of steel moving through the ocean without making a sound. Picture a vessel longer than a football field, carrying enough firepower to level a city, gliding through the crushing depths where sunlight never reaches, and pressure would instantly kill an unprotected human. Now imagine that this enormous machine is so perfectly engineered that enemy sonar systems simply can't detect it. That's the USS Virginia, and it represents a quantum leap in submarine technology that has defense experts and tech innovators like Elon Musk calling it decades ahead of anything else in the world. When Musk made a statement about America's underwater weapon being invisible, he was describing an engineering reality that most people don't fully comprehend. The Virginia-class submarines measure 377 feet in length. That's longer than the Statue of Liberty is tall. They can dive to depths exceeding 800 feet, though the actual maximum depth remains classified and is certainly much deeper. They can travel at speeds greater than 25 knots underwater, which translates to about 29 miles per hour. That might not sound fast compared to a car on a highway, but underwater, where water resistance is roughly 800 times greater than air resistance, that speed is extraordinary. But raw specifications don't capture what makes these submarines truly revolutionary. The Virginia-class represents the first time the United States Navy built a submarine designed entirely in 3 dimensions, using advanced computer modeling. Every pipe, every cable, every valve was mapped in digital space before a single piece of steel was cut. This approach eliminated the errors and inefficiencies that plagued earlier submarine construction. Traditional submarine design relied on paper blueprints and physical mock-ups. Engineers would discover problems only after workers started welding pieces together, finding that a pipe interfered with a cable run, or that a critical valve couldn't be accessed for maintenance. Those mistakes cost time and money, and in military applications, they could compromise the vessel's capabilities. The digital design revolution changed everything. Engineers could test modifications virtually, checking every system interaction before committing to actual construction. If the Navy wanted to upgrade electronics or reconfigure a compartment, designers could model the change completely, verify it wouldn't create problems, and then implement it with confidence. This flexibility means Virginia-class submarines can be upgraded and improved throughout their service lives, without requiring complete rebuilds. When Elon Musk talks about decades of technological advantage, he's referring to acoustics, the science of sound and how it travels through water. In submarine warfare, the side that hears the enemy first usually wins. The Virginia-class submarines are the quietest attack submarines the United States has ever produced, and that acoustic stealth represents an engineering achievement that took decades to perfect. Sound travels differently in water than in air. It moves about 4 times faster and can travel for hundreds of miles under the right conditions. Ocean layers, temperature changes, and salinity variations create channels where sound can bounce and carry enormous distances. A single mechanical noise, a pump vibrating, a valve clicking, a piece of equipment rattling, can announce a submarine's presence to listening stations thousands of miles away. The engineers who designed the Virginia-class understood that every component, every system, every piece of the submarine needed to be acoustically optimized. They couldn't just make the propulsion quiet and call it finished. They had to eliminate noise sources throughout the entire vessel, from the nuclear reactor that powers it to the smallest pump circulating cooling water. At the heart of the submarine sits an S9G nuclear reactor, a power plant that generates steam to drive turbines without ever needing to refuel during the ship's entire operational life. That reactor makes these submarines essentially unlimited in range. They can stay at sea for months, limited only by how much food they can carry for the crew. But nuclear reactors require pumps to circulate coolant, and pumps create vibration and noise. The solution involved mounting every pump on specially designed vibration isolators. These mounts act like shock absorbers, preventing mechanical vibrations from transmitting into the hull, where they could radiate into the water as detectable sound. The propulsion system represents perhaps the greatest acoustic achievement. Instead of using a traditional propeller with exposed blades, the Virginia-class uses something called a pump jet, essentially a ducted fan system that moves water more smoothly. The blades are enclosed in a ring, which prevents the formation of cavitation bubbles that create noise. The water flow is steadier and quieter, making the submarine far harder to detect even when moving at high speed. The innovation didn't stop with quiet machinery. The designers completely reimagined how submarines gather information about their surroundings. Listening to the ocean's secrets, traditional submarines used optical periscopes, long tubes running from the control room up through the hull to the surface, using mirrors and lenses to give the captain a view of what was happening above the waves. This design had been standard for more than a century, and it created significant limitations. The control room had to be positioned directly beneath the periscope. The viewing area was tiny, and only one person could look through it at a time. The Virginia-class threw out that entire concept. Instead of optical periscopes, these submarines use photonics masts, slim camera towers that rise through the sail but don't penetrate the pressure hull. High-definition cameras capture images and send them down via fiber optic cables to display screens in the control room. This seemingly simple change revolutionized submarine operations in ways that extend far beyond just having a better view. First, the image quality is dramatically superior. Instead of peering through a narrow tube that shows a tiny field of view, the crew can see panoramic, high-definition images displayed on large screens. The cameras can capture images in low-light conditions that would be impossible for optical periscopes, and they can zoom and enhance details that a human eye looking through glass and mirrors would miss. But the real revolution was what this change did to the submarine's interior design. With no optical periscope tube running through the ship, designers could move the control room lower in the hull, making it safer and more spacious. They could widen it, reorganize it, and optimize it for modern digital systems without being constrained by a single column of optics that had to sit in one specific location. Even the control mechanisms evolved in unexpected ways. The original Photonics mast was operated with a heavy helicopter-style control stick that sailors found awkward and uncomfortable during long observation periods. During testing, someone suggested trying a standard video game controller, the kind millions of people already know how to use. It worked better than the custom-designed military hardware, so the Navy adopted it. submarines operate in an environment where vision is nearly useless. Below a few hundred feet, no light from the surface penetrates. The ocean is pitch black, and visibility, even with lights, is measured in dozens of feet at best. In this darkness, sound becomes everything. The submarine that can hear farther and interpret sounds more accurately has an overwhelming advantage. The Virginia-class carries some of the most sophisticated sonar systems ever installed on a submarine. The early boats featured a large spherical sonar array mounted in the bow, a massive ball of sensors that could detect sounds from all directions. Later submarines replaced this with a large aperture bow array, a horseshoe-shaped system that's easier to maintain and provides even better acoustic detection in the frequency ranges most useful for modern submarine warfare. Along the sides of the hull run wide-aperture flank arrays, essentially two long ears that give the crew a tall, wide picture of the ocean's noise environment. Under the bow sits a high-frequency chin array designed for close-in safety and mine detection. Additional high-frequency panels in the sail help with tight maneuvering under ice or in cluttered coastal waters, where precision navigation is critical. Together, these sensors create a three-dimensional acoustic picture of everything happening around the submarine for hundreds of miles in all directions. But raw data from microphones isn't enough. The real magic happens in how that information is processed and interpreted. Ocean noise is incredibly complex. Biological sounds from whales, dolphins, and shrimp mix with geological noise from underwater earthquakes and volcanic activity. Ships of all kinds generate distinctive acoustic signatures. Filtering useful signals from this chaos requires enormous computing power and sophisticated algorithms. The Virginia-class combat system uses an open architecture approach, meaning the Navy can continuously upgrade processors and software without redesigning the entire submarine. As artificial intelligence and machine learning improve, these capabilities can be integrated into existing boats, making them smarter and more capable over time. This future-proof design philosophy is exactly the kind of thinking that impressed Elon Musk, who built his companies around the principle that hardware should be a platform for continuously improving software. But listening and hiding are only part of the mission. These submarines also need to strike with devastating precision. The arsenal beneath the waves. A Virginia-class submarine carries approximately 30 torpedoes and can fire up to a dozen cruise missiles, making it one of the most heavily armed vessels ever to slip beneath the sea. The primary weapon is the Mark 48 torpedo, a heavyweight hunter-killer that has been continuously upgraded since its introduction. The latest versions, designated ADCAP for advanced capability, feature digital sonar processing that makes them effective in both deep ocean and shallow coastal waters. What makes the Mark 48 particularly deadly is its intelligence. Modern versions can be launched on a guidance wire, allowing the submarine's fire control team to steer the weapon during the initial phase of the attack. Once the torpedo gets close enough to acquire the target with its own sonar, it can be cut loose to finish the hunt independently. The weapon can outmaneuver most targets, dive deeper than most submarines can escape to, and carries enough explosive power to break a ship's back or crack a submarine's pressure hull. But torpedoes are only part of the Virginia-class arsenal. From the beginning, these submarines were designed to strike targets on land, far inland from the coast. Early boats carried 12 vertical launch tubes in the bow, specifically for Tomahawk cruise missiles. These weapons can fly over 1,000 miles, navigating with GPS and terrain-following radar to hit precise targets with minimal collateral damage. Later production blocks of the Virginia-class moved to 2 large payload tubes up front, each capable of holding 6 Tomahawks. This change simplified the design and made maintenance easier while maintaining the same striking power. But the real revolution in land attack capability came with the Virginia payload module. Starting with Block V submarines, the Navy inserts an 84-foot-long section into the middle of the boat. This plug contains 4 enormous vertical launch tubes, and each tube can hold 7 Tomahawk missiles. That's 28 additional missiles on top of whatever the bow tubes carry, giving a single submarine the ability to conduct a sustained land attack campaign without returning to port for rearming. The addition of the payload module pushes the overall length to about 461 feet and increases the submerged weight to approximately 23 million pounds. These are massive submarines by any standard, rivaling the size of some ballistic missile submarines. Yet despite their size, they remain as quiet and stealthy as their smaller predecessors, a testament to how thoroughly the acoustic engineering has been refined. Operating a nuclear submarine requires a unique combination of technical expertise, mental discipline, and ability to function in one of the most demanding environments humans have ever worked in. A Virginia-class submarine typically carries about 140 crew members, roughly 18 officers and 122 enlisted sailors. These people live inside a steel tube for months at a time, breathing recycled air, eating food from storage, and knowing that any serious mistake could kill everyone aboard. The submarine operates on an 18-hour day divided into 6-hour watch cycles. This schedule, while strange to landlubbers, allows the crew to maintain constant vigilance without exhausting. Teams rotate through watch stations, manning the sonar room, controlling the boat's course and depth, monitoring the nuclear reactor, maintaining weapons systems, and handling the dozens of other tasks that keep a submarine operational. Life aboard is intensely regimented because it has to be. There's no room for casual disorder when you're sealed inside a pressure hull hundreds of feet underwater. Every action, every procedure, every response to every situation is drilled and practiced until it becomes automatic. Sailors learn to move through the cramped compartments without making unnecessary noise. The newest Virginia-class submarines include creature comforts that earlier generations of submariners would have envied. Better air circulation systems, improved water recycling that allows more frequent showers, and enhanced food storage that provides better meal variety. But make no mistake, this is still an incredibly demanding environment. Sailors go months without seeing sunlight, without breathing fresh air, without any privacy, and without the ability to simply step outside for a walk. What keeps these crews performing at such high levels is a combination of exceptional training, strong unit cohesion, and the knowledge that they're operating the most advanced underwater weapons platform ever created. There's pride in being part of something that represents the absolute cutting edge of human engineering and military capability. The Virginia-class built upon lessons learned from a legendary predecessor. The Cold War legend that paved the way. Before the Virginia-class rewrote the rules of submarine warfare, the Los Angeles-class ruled the depths for nearly 30 years. These submarines, first commissioned in 1976, represented the backbone of America's underwater fleet throughout the Cold War and into the 21st century. Understanding the Los Angeles-class is essential to appreciating just how revolutionary the Virginia-class really is. The Navy built 62 Los Angeles-class submarines between 1972 and 1996, the most nuclear-powered attack submarines of any single class in U.S. history. That production run speaks to both the design success and the urgent needs of the Cold War era, when American submarines played a high-stakes game of underwater chess against Soviet naval forces across the world's oceans. Each Los Angeles-class submarine measured roughly 360 feet long, displaced about 7,000 tons underwater, and could officially dive to depths greater than 650 feet, while traveling faster than 25 knots. Like modern submarines, the actual maximum capabilities remain classified and are certainly better than the publicly admitted specifications. At their heart sat nuclear reactors that gave them essentially unlimited range. They could stay at sea for months limited only by food supplies and crew endurance. The Los Angeles class went through several evolutionary phases that the Navy calls flights. The original boats carried 4 torpedo tubes capable of firing the Mark 48 torpedo, which remains in upgraded form, the primary submarine weapon today. Later boats added 12 vertical launch tubes for Tomahawk cruise missiles, giving them the ability to strike land targets without using their torpedo tubes. The final 23 submarines, called the Improved Los Angeles Class or 688I boats, received significant upgrades. Engineers moved the diving planes from the sail to the bow and made them retractable, allowing these submarines to operate under Arctic ice. The sail itself was reinforced for surfacing through ice, and interior machinery was better isolated to reduce noise. These improvements made the late production Los Angeles boats much more capable than the early models, even though they looked nearly identical from the outside. As of 2025, approximately 23 Los Angeles-class submarines remain in active service, forming a substantial portion of America's attack submarine fleet alongside the newer Virginia-class boats. While the Virginia-class represents the current state-of-the-art in submarine technology, American naval planners are already designing its successor. The program is called SSN, open parenthesis, X close parenthesis, and it aims to combine everything the Navy has learned from 70 years of nuclear submarine operations into a single revolutionary design. SSNX is still in the design phase, with construction not expected to begin until around 2040. That distant timeline is simply because shipyards are already fully committed to building Columbia-class ballistic missile submarines and continuing Virginia-class production. The Navy can only build so many submarines simultaneously without compromising quality or exhausting the skilled workforce. When Elon Musk evaluates technology, he looks for fundamental advantages that can't be easily replicated. As someone who revolutionized electric vehicles, reusable rockets, and satellite internet, he understands that true technological leadership is about achieving breakthroughs that reset the competition's timeline by forcing them to start from scratch. The Virginia-class submarines represent exactly that kind of breakthrough in underwater warfare. Other nations certainly build capable submarines. Russia, China, Britain, and France all operate advanced nuclear submarines. But the combination of acoustic stealth, sensor sophistication, weapons capacity, and operational sustainability that defines the Virginia-class creates a capability gap that would take competitors decades to close, even if they fully committed to the effort today. The Virginia-class submarines represent more than just advanced military technology. They're proof that sustained investment in engineering excellence creates advantages that competitors can't quickly replicate. When Elon Musk describes these vessels as decades ahead of rivals, he's recognizing an achievement that combines breakthrough technology with institutional knowledge built over generations. What other invisible weapon systems might America be developing right now beneath the surface of the world's oceans? Share your thoughts in the comments below.